Sorry for the delay. I'm just making sure that the stream is working. Okay, perfect. Hi everyone. It's a pleasure to welcome our speaker, Rana Hanocka, today. Rana is an assistant professor of computer science at UChicago. Before this, she did her PhD at Tel Aviv University under the supervision of Daniel and Raya. And during her PhD, she won numerous awards for her research, including the Dan David Prize Scholarship in 2020 and the Outstanding Data Science Fellowship. At UChicago, Rana leads a group working on the intersection of 3D and deep learning. And this is really an emerging intersection where she has been at the frontier for many years from her graduate school days. And today we are very excited to hear her latest and greatest on this. Rana, please take it away.
Thank you. Thanks for the nice introduction and thanks for the invitation. So as Shubham already mentioned, I have a new group at UChicago. We're called 3DL. We look at problems at the intersection of 3D and deep learning, and we definitely have some exciting stuff going on that I think you should keep a lookout for. One thing that we're currently looking at that I'm pretty excited about is we're able to take 3D meshes and automatically stylize them. So we don't need any training data or even a texture map. So if you want to know more, I'd encourage you to check out our group's website and follow more closely what we're up to these days. So onto the main part of my talk. We're seeing 3D data being used more than ever before in many different fields: manufacturing, medicine, entertainment, but the demand to create these models is growing faster than we can actually construct them manually. And one way we might think about obtaining a digital 3D model automatically is by scanning a real world object, but this requires a processing step to reconstruct the underlying surface. But surface reconstruction is actually a notoriously difficult problem. To make things even more difficult, the point samples themselves are never perfect. There's noise and outliers, regions with sparse samples or holes, and we don't have enough points on sharp features, which will ultimately lead to undesirable reconstruction results. And if the point normals are unoriented, we must first orient them before reconstructing a surface. Today, I'm going to talk about 3 different neural reconstruction works. The first work consolidates noisy point clouds. So that means remove noise and add new points. Another learns to estimate a globally consistent normal orientation. And the last work reconstructs the underlying surface directly from noisy and imperfect scanned input data, and it can even handle unoriented normals. In this next part, I'm going to focus on these 2 works, and their similarity is that they both learn from the internal data within the single given corrupted example for reconstruction. And this is different from the most popular use of deep neural networks, which involves training them on big data. And that requires really large external data sets. But this is actually really hard for 3D because it's difficult to obtain a large amount of geometric data that's sort of usable for us, which means watertight and manifold. And even if this geometric data is usable, it's still very inconsistent. So the same exact shape can be represented using many different underlying sort of meshes. And this type of inconsistency is going to make learning difficult and challenging. So I think it would be very useful to be able to sort of bypass having to collect and annotate and learn from these large and complicated 3D data sets Instead, I think that we can actually learn from the internal data that's given within a single 3D shape. And this is without having to pre-train on any external data sets. And this is possible because there is a lot of internal data within only a single shape, because shapes can have repeating structures or elements. They often have symmetries, and more generally, it's just possible to represent a shape with a small number of local patches. And this implies that similar patches must repeat within a single shape. And so what I'm getting at here is that there is a lot of useful patch data, which is unique to this particular shape, and I think that we can leverage and learn from it. We call this idea of learning from the internal data on a single example using a deep neural network, the self-prior. And we train a network on the given internal data in this single noisy input during test time, and the inductive bias of neural networks with shared weights results in desirable solutions. And I want to emphasize again why I think this idea is really cool, because normally we would need to model a 3D scanner, the 3D scanning acquisition process, and that would enable us to generate some sort of supervised external data to train on. But there's a lot of different types of scanners, and they all have very different statistics, and these statistics are difficult to model. And of course, training on one doesn't necessarily imply that we can sort of generalize this on another scanner. And the self-prior, it bypasses the need to simulate large amounts of external training data from a particular distribution. And instead, we can just train on this internal data given in a single input during test time. So let's talk about how we use the self-prior to consolidate point clouds. And this means remove noise and generate new points. And this is going to be a pre-process to surface reconstruction. The kind of key idea here is that we train a neural network on the internal data within this single given input point cloud, where we exploit this simple fact that we can select many different pairs of these global subsets from this one input point cloud, and then we can train a network to repeatedly learn a mapping from one randomly selected subset to another. And this is going to implicitly remove noise and outliers in the given data. So when we're done training, we can feed many random subsets to the network, and this will generate an arbitrarily large amount of noise-free points. And I think that this result is pretty amazing because given only the noisy input itself, we're able to output a cleaner and better version of the underlying shape. And this is again due to the fact that the network doesn't have the capacity to predict noise or outliers, and that's exactly the effect of the self-prior. And here's what the reconstructions look like. So the way that we do this is we loosely partition the points into sort of source and target groups. And this is based on some desirable consolidation property. So in this case, it's sharp features. And the way that we sort of roughly approximate sharp is by looking at their approximate curvature. And this really simple definition of sharp is actually sufficient because networks are good at understanding the core modes of the data, and they just kind of implicitly ignore outliers. During training, we repeatedly sample global subsets from this single input point cloud, where we rebalance this target subset to contain mostly sharp points. And then the source subset will contain a much lower percentage of sharp points. And then we train the network to displace the source subsets such that they resemble the target ones. And our loss here is just a bidirectional temporal distance between both of these point sets. So now that we've finished training, we can just use this neural network and feed many random subsets to it and just continue to aggregate this arbitrarily large amount of noise-free points. And the points will have some type of emphasis on the criteria that we kind of predetermined. So in this case, it was points on sharp features. One thing that's unique about this work is that it operates on global subsets. So this will kind of encourage learning some type of non-local information. So say you take this input, which was obtained from a LiDAR scanner, and you can see these kind of undesirable sampling patterns. And if we train a network to sort of overfit on this like one local patch, you'll see that these real overfitting sort of results, right? Like the yellow is kind of exactly fitting to this arbitrary pattern here in blue. But if we train the network on global subsets, then the shared weights will kind of exploit this redundancy in a single shape. And we're going to see a more plausible solution that can't really overfit to these artificial patterns. Here, so the desired consolidation criteria is sort of, can be anything. And another thing that we showed in the paper is that we can add points in sparse regions. So that would be part of the target subsets. And in that case, we can add more points in sparse regions. And when we use this consolidated point cloud as input to some off-the-shelf surface reconstruction algorithm, we're going to see much better results. And this is just something, an off-the-shelf surface reconstruction algorithm, but now I'll show you how we can actually directly reconstruct the surface using the self-prior. In point-to-mesh, we use the self-prior to reconstruct a surface mesh directly from scanned data. And we use the internal data within a single given input point cloud to leverage this self-prior for reconstruction. So concretely, how does surface reconstruction work? It's given a set of points sampled from a surface of an object. We aim to recover the underlying shape. But this is actually an intractable problem. It's been studied extensively for 20 years. Let me show you what I mean with a much simpler example of only a few points. So there's actually infinitely many curves or surfaces that will pass through these points. And another way of saying this is the problem is ill-posed. If we want to pick a favorable solution or reconstruction result, this is going to require designing some type of prior, which is going to capture the expected shape properties. But building this prior is really challenging, especially when shapes are going to be much more complicated than this very simple example. The conventional way to sort of handle this is to define some generic smoothness prior for reconstruction. But as you can see here, this will reconstruct holes in a way that's going to ignore the character of the global shape. A handcrafted smoothness prior is too generic to tailor itself to any one particular shape. On the other hand, we do tailor the self-prior to each individual input using the neural network that's trained on the internal data given in this corrupted input itself. And this is exactly the effect of the self-prior. The self-prior produces a more plausible reconstruction because it learns the character of the global shape. And this is really effective when we want to complete missing parts, remove noise, and so on. The CNN that we used in this work relies on an earlier work of ours called Mesh CNN. And that's a technique for applying CNNs on triangular meshes. And the key sort of insight there is that every single edge in a manifold triangular mesh has a fixed size neighborhood of 4 edges. And we essentially learn deep features over the edges of a mesh, and then we can do sort of any learning tasks. And in the mesh CNN framework, we have convolution, pooling, and unpooling operators that are applied directly over the mesh edges. And here in point-to-mesh, we leverage these operators to learn the self-prior. The way our self-prior works is by shrink wrapping. So we start with some input point cloud and some initial mesh, and then we iteratively optimize some mesh CNN weights to deform this initial mesh to shrink wrap the input point cloud. And this strategy is actually very appealing because it will give us all sorts of geometric guarantees, like ensuring our reconstruction is watertight and manifold, and it can even preserve the genus of the shape. And because of these desirable properties, shrink wrapping has been attempted many times before, but these attempts were considered unsuccessful. They required manual tuning or intervention to work on different shapes. And so what's cool about point-to-mesh is that we can successfully perform this shrink wrapping in a more robust way by leveraging the power of neural networks to learn from internal data. These optimized CNN weights, they are what act as the self-prior, and they encode the expected shape properties. The key to this self-prior is this unique structure of a convolutional neural network. On the one hand, these convolutional filters are applied locally, but on the other, these same exact local filters are shared over the entire shape. And the premise here is that shapes are not random, right? They contain strong self-correlations across multiple scales, and they're very piecewise smooth. So the way point-to-mesh works is as follows. We start with some input point cloud, and we use that to calculate some initial mesh. If we know the genus of the initial mesh is 0, so we can use a convex hull to calculate this initial mesh. And for non-zero genus shapes, we can use other techniques, and I'll talk about that in some later slides. Then this initial mesh is used as input to a mesh convolutional neural network, and this displaces the mesh vertices, which will result in a deformed mesh. And then this deformed mesh is sampled to obtain a set of points. And then we calculate the distance between these two sets of points. And this distance is used as a signal, and that's what's going to update the mesh CNN weights. And we iteratively perform this update where in every iteration, the mesh is going to more closely approximate the input point cloud. So the way this works in a bit more details is that we start with some initial deformable mesh M, and that defines our adjacency information. And we're going to use that to apply convolutions and pooling in mesh CNN. But in mesh CNN, we had sort of geometric features over each edge that we started with, and the network learned to abstract those to something meaningful. Here, sort of take inspiration from work called deep image prior, where we just assign a fixed random tensor of per edge in the mesh, and then we just train the network to take this sort of random fixed value and learn the self-prior. And so because these mesh CNN networks, they operate on edges, the network will abstract these random features to a displacement vector per edge. But we actually want to displace the vertices of the mesh, right? So the idea here is that for every single vertex, we average the edge displacements. Let's show the animation here. Oh, here we go. So for every single vertex, we average over the edge displacements over each of the incident edges, and this is going to result in some displacement per vertex. And then this displacement is added to the initial, the vertices of the initial mesh, and this is going to result in some estimate of the reconstructed mesh. And because we make this displacement differential, then we'll initialize these weights to be 0 in the first iteration. And then when we do this reconstruction in the first pass, we're just going to get something that looks like the initial mesh. This reconstructed mesh will go through a differential sampler. And first, the sampler will randomly select a triangle, and that's going to be proportional to the face area. And then we randomly select a point on that triangle, and that XYZ location is defined by the 3 triangle vertices. And this is how gradients will be ultimately backpropagated through the sampler to update the CNN weights, which will displace the vertices. Then we compute the loss by comparing the sampled reconstructed mesh to the input point cloud. And the way we do this is we take the bidirectional transfer distance, which means for every single point in the reconstructed mesh, we take the distance to the closest point in the input point cloud, and then sum it, and also sum the distance from every single point in the input point cloud to the reconstructed points. And based on this transfer assignment, we also have unsigned comparison of the normals from the input point cloud and the reconstructed mesh. In practice, we do a course-defined sort of optimization with this framework. So first, we use some low resolution initial mesh, which is roughly a few thousand faces, and then we'll run 1,000 iterations of this procedure. We'll get some sort of initial guess. We'll pass this mesh to a robust watertight manifold technique, and then that will also slightly increase the resolution and smooth the result. And then we throw away the old network, we initialize a new network, we initialize new random tensor for this higher resolution mesh, and then we rerun the optimization again for 1,000 iterations. And then we just repeat this procedure until we've reached the desired resolution. I really like this example because it illustrates how the network acts as a prior. So if we directly optimize the mesh vertex locations instead of the convolutional neural network, we're going to be trapped in a local minima. But if we optimize the mesh CNN weights to displace the mesh vertices, then the mesh will enter this difficult second order cavity. And you can see here exactly how the network acts as a prior, right? It gives us something that's different from this trivial sort of mesh optimization. The self prior is going to help us avoid bad local minima, and this is the key to the success of point-to-mesh. The previous works that tried this type of shrink wrapping, they couldn't design a powerful enough prior to avoid these local minima in a more general sense. And I think it really demonstrates the power of mesh convolutional neural networks with inductive bias and the internal learning. Here's another example of how the self-prior convergence looks like. So here you can see low density sampled regions are still accurately reconstructed, it doesn't sort of enter inside. And this is another example of that. And here's another example with a pretty high, relatively high resolution mesh, which contains much finer details. So we also used point-to-mesh to reconstruct objects that we scanned with a real 3D scanner. And even though there was some noise and low density patches where we the scanner didn't really sample the surface properly there, our reconstructions will still handle these regions well. And those geometric guarantees I mentioned before, they really come in handy because it will enable us to, for example, 3D print this object. We compared against existing techniques on the task of denoising. So the most popular method for surface reconstruction is Poisson surface reconstruction. And this uses some type of smoothness prior. And in this case, it overfits to noise. Point CleanNet is a data-driven deep learning technique for denoising point clouds. And we just apply Poisson surface reconstruction afterwards to visualize what the result looks like. Deep geometric prior also learns a reconstruction from a single shape, but it has a few differences compared to our technique. So first, it optimizes local patches to the point cloud, and so it won't generate some watertight surface. And because each local patch is sort of optimized separately, there's no notion here of shared weights. With our self prior, you can see that the noise is sort of naturally removed, and this will work better than traditional smoothness priors or networks trained on external data. We also compared against these same techniques for the task of handling missing parts. And existing techniques don't utilize or consider any sort of genus information, so they can induce some type of topological error, and that will mean that they can reconstruct a surface with the incorrect genus. And without this global weight sharing over a single watertight surface, it might be difficult to properly fill holes in a shape. But with our method, the genus is provided implicitly, and this is through the initial mesh. And so this gives us some type of control, and it can be seen as an advantage for hole filling. In this example, Poisson will reconstruct a surface with incorrect topological holes. And so what we did is we applied a low resolution octree to close these incorrect holes and create a coarser mesh, which we used as an input to, as an initial mesh to our technique. And the result is a topologically correct mesh, which preserves the details from the input point cloud, but still doesn't overfit to these incorrect low density regions. So using this coarse mesh on the result of Poisson reconstruction is one way that we can sort of handle this issue of meshes with unknown genus. Point to mesh can also handle unoriented point normals, and I'm going to discuss in depth in the next section all about that. But here, I just want to show that we estimate unoriented normals in the input point cloud. And so we color each point with the angle error. And you can see that existing techniques, they're going to be very sensitive to these incorrect normal orientations. And that's going to produce undesirable artifacts. But our approach is agnostic to normal orientation. So I think this is another really powerful aspect of point to mesh, because an unoriented normal is a prerequisite for surface reconstruction, and we kind of just bypass this need altogether. Both of these works demonstrate how to leverage the internal data within noisy scans to learn a self-prior for reconstruction. Just from the internal data in the single given noisy input, we're able to generate many noise-free points and solve a challenging global shrink wrapping optimization. So now I'm going to switch gears, and I'm going to talk about a new work that Gal just presented in this past SIGGRAPH, which focuses on the normal orientation problem. When we obtain a point cloud from scanners, it can lack normal information, or if we are processing or editing the point cloud data, we need to recompute normals, like during consolidation. And recently there's been a sort of new source of point clouds that lack oriented normals, and that's network generated point clouds. But normals are required to do things like render point clouds, voxelize volumes, sign distance fields, and reconstruct a surface mesh. A normal is a vector that points perpendicular outwards from the surface, and we calculate it by fitting a plane to nearby points. And this normal is correct up to the sign of the vector or the orientation. We say a normal is oriented if all normals point outside the surface. But since we fit local planes, we don't know the, sorry, there's a, I guess skipped here by accident. Yeah. So a normal is oriented if they all point outside the surface, and these here are not pointing outside the surface. But this requires global context. So when we look at a patch of a shape in isolation, determining whether it points, this patch points inward or outward is completely ambiguous. In this work, we developed a method for orienting point normals, and the results are shown here with, again, the angle error shown with the heat map. And you can see how, again, the surface reconstruction is very sensitive to point normals with incorrect normal orientation. So we divide our approach into two phases, a local phase and a global phase. First, we break up the shape into local patches. And then in the local phase, we train a network to learn to estimate a coherent normal direction per patch. And when I say that, I mean it's a consistently oriented normal within a single patch, but that's up to the sign. Okay, so all normals within the patch, they agree with each other, but it's not necessarily globally consistent. And then in the global phase, we will propagate across all of these coherent patches using a dipole propagation. And I think this approach is interesting because we let the network intentionally handle the really difficult and highly non-convex cases. And then we use a robust dipole propagation to propagate this orientation to all the patches globally. So the way the local phase works is we train the neural network to predict a coherent orientation per patch. And so in this case, that means all the normals are pointing in sort of agreement, either so-called inside or outside, although it's not defined at this scale, right? And so what we do is we train the network to predict a probability per point, like given points and normals as input, that the normal should be flipped. But the problem is that there's actually two equally valid ways that we could have coherently oriented this patch, right? We could have flipped this subset, or we could have flipped the inverse of that subset. And so basically we have two ways that are equally valid for coherently orienting these patches. And training on both would make the network objective discontinuous and oscillatory, and this is not really ideal. We create a better and more smooth training objective by uniquely determining a single solution for each input point cloud by looking at the majority direction of the input normals. So we always aim to predict a high flip probability for the smaller subset and a low flip probability for the larger subset. And then we train the network to learn to flip the smaller subsets of input points. And if we inverted the normals in this patch, so the network should predict the same exact flip probabilities. And now that we've coherently oriented all of the patches in the local phase, we propagate the global orientation iteratively to all the patches. We start by selecting some planar patch, and then we treat each point in the patch as an electric dipole with polarization that points in the normal direction. And here is the electric potential that's dissipated by the dipoles. So blue and red will eventually correspond to regions in space which are inside or outside the shape. We measure this interaction between the electric field and the normal of each point left to be oriented. And you can see the highest interaction here. So the length of each of these lines is proportional to the interaction value. We select this patch and we add its effect to the total electric field. We continue to add each patch and possibly flip it until there's no more patches left to be oriented. And here's a more complicated shape so you can see how it works in practice. You can notice that the propagation doesn't necessarily move to nearby patches, which is like the common approach using minimum spanning trees. So it propagates based on the field, which may not be nearby. So we kind of leverage this nice property here that this electric field is robust to some noise or incorrect normal orientations. This will only kind of degrade things locally around the electric potential. So our global electric field is still going to be robust to some errors that may arise from the network or noise or something ambiguous. And the way that we leverage this is by enabling this sort of global stable field to correct any lingering errors, and we call this diffusion. So we reevaluate the interaction of every individual point with this global electric field, and points that don't agree with the field are individually flipped. And this step is helpful to fix any local errors, again, that may have been predicted by the network, or and so because during our correction procedure, we only flip entire patches. So if there's one error from the network, we will not be able to fix it during that phase. So in this phase, we can do some corrections. So both of these steps, the network predicted scores, are actually used during diffusion, during propagation, and the network predicted probabilities as well as the diffusion are both important. So if we don't use these network predicted probabilities to weight the dipole propagation, then we get too many errors, which the diffusion step is not able to fix. But on the other hand, if we don't use this diffusion step, so the network predicted confidences still can't fix the lingering errors that may be left over. So our method is able to scale to millions of points. And here's some examples of that on some corresponding reconstructions compared to existing techniques. And here are some techniques that use the minimum spanning tree. So again, they kind of, when they fail, that they're sort of locally greedy, and so they'll end up with these pretty significant errors. Whereas our technique is robust to these sort of issues. So basically in this work, we have two kind of main things. One is the network learns to predict a coherent direction of normals that all sort of agree with each other on local patches. And the second phase propagates these coherent patches using dipole propagation. And some take-home messages from this talk are that we can use the self-prior for reconstruction and learn from the internal data within a single shape. And we also showed that we can use a data-driven technique to solve a complex local problem. And this is effective when we combine it with a global robust propagation technique. I'm interested in using this self-prior for other problems in geometry processing, like for deformations, animation, shape editing, and so on. I think a combination of data-driven neural networks and robust optimizations can be a really effective way to learn on geometric data. And we're looking at applying this to tasks in texture mapping and shape manipulation. But beyond just reconstruction, I'm excited about a lot of other topics related to 3D and deep learning. Just to give you an idea, so one thing I think would be very exciting is to train networks to learn to correct, edit, and manipulate mesh connectivity. Like, can we generate meshes with sharp features that are kind of, aligned to sharp edges? Can we fix non-manifold geometries, close boundaries, and do other things? And of course, I'm interested in seeing if we can do this with a small amount or even no external data. Another thing I think is really interesting is to look at identifying patterns and structure and relationships in shapes. And analyzing these patterns could enable us to generate more variations from a small amount of shapes. So you can imagine this would enable us to generate sort of more of the same. And I think it will be cool to achieve some sort of higher level editing tool where we can think about how to incorporate and mix elements of one object with another such that one shape can take on the style or functionality of another. And this is even across completely distinct shape categories. So thanks for listening, and the code and the papers are available on my website and my group's website. And if you're interested in working on some of these or related problems, please feel free to get in touch.
Yeah, great. Thanks, Rana, for a wonderful talk. Yeah, I know we all have a few questions, but actually I'll start with one from the audience before we get to the questions that we have. So Vadim Kontarov on YouTube was asking, more related to the first part of your talk, on when does internal prior learning break, sort of at what level of noise, and if you could give any insights on that.
Yeah, so I mean, I guess it's difficult for me to ask interactively if they were referring to the consolidation work or the reconstruction one. So let me think about both. So for the consolidation,
judging by the timing of the question, it maybe came out after the reconstruction work.
Oh, okay. So yeah, there's definitely some like significant sort of places that are not robust. So one thing is really thin sort of surfaces or sheets. Yeah, it's like a very special, like plants, you can imagine, things like that. I don't think this will work super well there. We haven't really extensively tried it out on those types of things, but from the little things that we did see, maybe with like very thin planes, that could be like sort of problematic. It will like fold over itself a little bit. So that's one thing. Another thing is that so if we know the genus is 0, so we kind of have this robust way to calculate this initial mesh. But if the genus is now something arbitrary and we don't know what it is, then we rely on Poisson for the most part, reconstruction, and Poisson is not perfect, of course. So we're kind of like, on the one hand, it's like a catch-22. On the one hand, we have the control over the genus and we can provide it as input. On the other, if we can't calculate it effectively or accurately, so then we'll like never be able to sort of overcome that.
Okay, thanks. And so there's another question, which is, I think you just mentioned Poisson, maybe you could expand on this, but how do we determine the initial mesh for shrink wrapping?
Yeah. So we looked into a couple different techniques and none of them were perfect. But we found that the most robust one was Poisson. But Poisson, so the way we use Poisson is we take, we use it to reconstruct the surface and then we coarsen it a lot. Like I showed in the slide, I don't know, probably take a while to go back to it, but we coarsen it a lot so that it's not kind of already tightly fit to holes and noise. So, and then we can use that as kind of an initial starting guess. That was the most robust thing, but Poisson also has some failure modes, also with very close sheets. And yeah, like nearby surfaces and things like that.
Okay, thanks. And actually sort of a follow-up question from Vadim was, does the quality for internal learning depend on the input sampling resolution? So I'm assuming it is a question about the resolution of the point cloud that you take as input and how does that factor in?
Yeah, so for reconstruction, like I guess we have some sort of bound on like Nyquist, right? Like if you're not sampling the features or the underlying surface in the right way, I suppose there's probably kind of no way to necessarily prove that you can reconstruct it properly. In practice, I don't know that we observed too much of an issue with a small number of points. Yeah, that wasn't a big concern.
Okay. So while we await maybe more questions from the audience, I'll give a chance to the panelists to ask, maybe starting with Or if he has any questions.
Yeah, great talk, Rana. Always
Thanks.
wonderful to see you your research. Yeah, I was curious about, I guess there's this balance between how far we can go with, inducing like priors without any data, right? And you came up with a few ideas on, here's the type of consolidation we'd like our network to be able to learn. But in some sense, what deep learning is telling us, sometimes it's hard to define things mathematically, and it's easier to show the network examples. Do you see any thoughts on how to incorporate synthetic data for that, for example?
Yeah, no, I think it's a really good point. Like, there's only so much we can infer from like a single example. Like if you're missing a complete half of a chair or something, there's no way for you to like complete that in a meaningful way because, well, how would you know? Whereas if you had a lot of data, so the data could tell you, yeah, these things are usually symmetric. There's usually something else over here. And so I think when it comes to, I want to say like, when you want to leverage something that's shared across a collection of data, like symmetries and stuff like that. So it seems like incorporating that knowledge somehow is useful. I guess I personally felt that it's been difficult to train these networks, right, on like the sort of state of the art in text and images requires things that we don't have. And so for me, I guess I've been trying to think about ways that I can still do interesting things, still solve interesting problems without necessarily having to have the data. But yeah, I think one thing that we've been looking into recently is maybe kind of combining like 3D and 2D, maybe using like differentiable rendering to get 2D information and kind of backpropagate that to 3D. And then you can maybe leverage some good properties that you get from images. But yeah, I don't know. It's a good question.
Maybe, just kind of delving deeper into this, the self-prior thing, right? So I know that you mentioned like deep image prior and deep geometric prior. A lot of these methods, they need some sort of like early stopping, right? And you mentioned that you use the mesh CNN, which is another great work by you, to do that. Correct me if I'm wrong, but I was worried when I looked at this that maybe when you give up on an edge, there's no way back. Is that risky somehow?
Yeah. So that's an interesting point actually you bring up. So what happens with deep image prior specifically, and I'm not sure if it also happens with deep geometric prior, but I assume so because they are doing these local patches, is that they notice that they have to, at least in deep image prior, do early stopping. Otherwise, they start to actually be able to predict the noise. In point to mesh, the surface mesh is actually another smoothest prior because you have these flat triangles, piecewise smooth triangles. And so you can't just like bend them over anything arbitrary. And so we noticed that actually there wasn't some sort of no going back in terms of noise, at least the types of noise that we look at, we didn't see it. But one thing that can happen is with like completion. If you have a very big hole and you're trying to shrink wrap it down, I think eventually if you train it enough, it will go inside of there. Although not always, but like that definitely seemed like the place where it could potentially fail with not an early stop. But yeah, that's a good point.
Can I steal one more question, Shubham, or am I?
Yeah, sure. I think
I don't want to hijack the questions, but I think it's hard to see talk about reconstruction using like meshes and explicit methods without asking, where are all the implicit methods coming into play here? What are your thoughts on? Because you talked a lot. I mean, eventually, in some sense, concepts about priors being baked into the network architectures, are manifested in this work as well. And I guess neural, like implicit representations, are all about baking priors into the network because there's not a lot of other places to bake priors into. Right?
Yeah. I think, I think NERF is like very exciting. It's very cool that you can do these kind of implicit reconstructions with no data, and it's just like the network gives you the smoothness stuff. It feels like the self prior in a way. But I think there is an advantage to have. So there's a time, I guess there's a time and place for everything. Like I think people are trying to like, what's the representation to win them all? And I don't know that there is one. I think, you have a specific task, and then you have a prior, like some domain expertise, and you want to do something specific. And so then the best representation is probably related to that task. So the task of NERF, reconstructing this like arbitrary scene and like complex genus, implicit does seem like the right way to go. On the other hand, if you have some prior information about like the topology of the shape, like the genus, trying to reconstruct a brain, it should have no holes in it, I think. So you can enforce that sort of information in the reconstruction. And I think, NERF or implicits in general, you have to do any right. I think even to a lot of, at least deep SDF works, right, to render those, I think they're actually extracting the mesh and then rendering it. So if you want to do some type of editing or usually fast rendering, you're going to use a mesh. But maybe some combination of them could be interesting.
Excellent points. Thanks.
Yeah, thanks for the question, sir. So I have a feeling Tushing might have some high-level questions. So before those, I want to sneak in a low-level question.
One high-level question about topology, right? So nice thing about the triangular mesh is that if we know the topology of the reconstructed model, then this is a strong regularization. For example, in implicit surfaces, right? So the topology can change, right? So but in in your network, right? So you can fix the topology. But what about, for example, the topology of the initial mesh could be wrong, right? In some cases, or maybe you don't know that, or maybe you want to make the topology be adaptive, right? So, what are your thoughts on this?
Yeah, no, I think it's a good point. Like if you really don't know what the genus is and you don't have a prior for it, and you think it will be difficult to calculate, then there might not be a particular advantage of doing it in this way. Because you could just take an implicit and implicit will give you something. Or you could use an implicit and say, I have like some rough notion of what I want to reconstruct. And then maybe you can kind of leverage that information and then use something like point to mesh and kind of enforce it in that way. But yeah, like it could be interesting to combine them, sort of like use each other to make like decisions maybe about like what the proper topology like should ultimately be. Yeah.
Okay. So I have another high level question, right? So for example, like in terms of the reconstruction problem, so sometimes we have this kind of unorganized point cloud, right? So that is what it shows. But in some other domains, like in particular in medical images, we have this kind of like scans of those cross section, right? So in fact that people have studied non-deep learning techniques to do reconstruction from those cross sections. And have you thought about applying your technique to there? Because I think, for example, human organs, right? So we do have some knowledge, right? Knowledge of the topology, right? So those one. Have you thought about those? Right?
We've been thinking about this for a little bit, because there is this kind of domain knowledge that you know what your scale, you know the organ that you're going to look at, and not just in biomedical domains. Also, there's like kind of like crystals, like really small microstructures where you kind of know what the thing you're imaging is going to look like in terms of its connectivity. So I do think that there is an interesting way to kind of put this into those applications. But yeah, I don't, other than I think that it's the right thing to do, I don't really have anything like more concrete to say other than like it would be interesting to try.
Okay.
Great. Thanks, Xisheng. So I also had maybe one low-level question before moving on to some of the meta ones. So one of the results in the first half of the work that I was really blown away by was this cat that you were reconstructing from a point cloud, and particularly looking at the legs. In the initial stages of the optimization, the legs were sort of connected. And then magically in one later stage, sort of that edge sort of almost disappeared.
Yeah.
And maybe wanted to understand that in a bit more detail. Was an edge being deleted in some way, or was it that because more vertices were created, some of them sort of moved up to sort of touch the body?
Yeah, that's exactly right. So basically what happens is if you have these kind of like legs and you snap something below them, sort of like stretched over them like a drum or something, if the triangles are really large, so it's hard to deform them to move inside. And so that will happen like during that's kind of why we do it in a course defined way. So we start with some guess, we move the triangles around, and then we kind of like remesh it to get more triangles in strategic areas. And then that enables us to go inside shapes.
I see. So to expand on that a bit, when you say get more triangles in strategic areas, sort of the upsampling, I assume then wasn't that let's double the resolution of the mesh, but more targeted that these are really stretched triangles and let's add more things here.
I guess from a practical perspective, it wasn't targeted, but I think from an intuitive perspective, it sort of, we added more triangles. It is specific to the initial, like the current deformed version of this. So the current deformed version of this actually has a certain curvature and certain shape. And so that's going to define where the triangles are going to be added, but we didn't necessarily explicitly like require it in a certain way. It just kind of fell out of the
Okay.
technique that we're using.
Okay, cool. And the other question I had was maybe trying to relate the first half of the talk with the second one. So in both of them, there was this commonality that you are learning this network, which is hopefully correcting noise through its structure. But maybe one of the differences that stood out to me was that in the first half of the work, there was this very explicit surface prior, that there was this surface that you are trying to fit to data to get the properties you desire. In the second half, even though you are estimating normal, by definition, surface properties, there was no explicit surface that you were still reasoning about on the side. And just curious on why this shift, or is it because just to handle millions of points that makes things more tractable, or some other reason?
Yeah, I think we were kind of interested in trying to look at solving the normal orientation problem. Like we didn't necessarily think, we actually used, I think, point to mesh as like a comparison there to see like how it could handle these cases. And it turns out the cases that are really difficult to orient normals from are point clouds that are generated from these GANs, because they were points sampled from shapes that have interior sheets. So you have all this stuff happening inside of the surface, and then orienting the normals is really hard, like near impossible in those cases, like ambiguous basically. So those were the really, really hard cases that we found, and like point to mesh did do quite well there, and so did this technique. So yeah, we just kind of wanted to look at, I guess, another problem.
Okay, great. So actually moving on to slightly higher level question and not necessarily related to reconstruction. So like you had this great work on mesh CNN a few years back, and in vision, or sort of more in 2D vision, there has been this trend of using less and less convolution in favor of maybe slightly more general operations like transformer based ones.
Yeah.
So do you think we might witness similar trends in 3D, and if so, what might they look like? Because yeah, right now still for meshes, I would say convolutions is maybe the predominantly popular approach.
Yeah.
And what may the alternates look like?
Yeah. So it's interesting you asked that, because when I look at transformers, I feel like so I can't argue with the results on images. I mean, they're amazing, but I feel like they're better suited for data without structure, like meshes, images have this nice structure. Why throw that away? I don't know, maybe they can leverage like some still inductive bias of the like grid, but it really just like, right, it treats it like a set. And meshes, we actually are unstructured, it's irregular, unordered, and so it seems like it could be a very good fit, actually, for geometry, even more so than images, but I guess it's just a matter of time.
I also want to give Qixing and Nor another chance to see if they have any broader questions.
So I would like ask regarding, for example, the fundamental challenges, for example, this kind of training data, right? So what is your thoughts on this kind of, like really pushing the 3D learning, right? What are the really fundamental challenges? Do you think we need to develop better neural networks models, or we need to think about having the next generation of data sets for boosting this kind of research in 3D learning, right? So because there's some, like originally, like for example, in the data science, we saw like big data, right? So now I think the community asks like we want good data, right? So for training, right? So the company that have the good data, they tend to win, right? So in industry. So what is your thoughts on in terms of this kind? Do we need more data? better data, or we still want to really push the neural network front?
Yeah, I think so. On the one hand, it's kind of a little bit of a conundrum because ImageNet was this data set that I think allowed the field to move forward, right? Even though today maybe people are more interested in unsupervised, self-supervised type methods, the ability to implement and prototype things first in a supervised way, I think help people see through some ideas that maybe they wouldn't have otherwise been able to understand were feasible. So from that perspective, it's like we kind of do need some data to be able to test things in the same way. On the other hand, I think we'll probably reach some like ceiling pretty quickly where it's going to be hard to make progress by just assuming that we should always collect more data and annotate it. So I think, I guess in parallel, they kind of need to happen right now. It seems like, at least in the world of 3D, but I personally feel like it will be a little unfortunate if the only way we can move forward is by always collecting data, but that does seem to be the thing that is giving the most, or some of the most incredible results. Like, but you know, there's things like NERF, which are kind of showing amazing things without data. So.
Okay, I have another high-level question. Thinking about the for example, the geometry processing pipeline, like from reconstruction to processing analysis to printing, right? So I think the two papers you mentioned, they actually belong to the geometry processing pipeline, right? For example, orienting points with normals to do then you have this reconstruction. So what is your general comment on this kind of the impact of 3D deep learning on this kind of geometry processing pipeline? Certainly, we see a lot of works on this reconstruction part, right? Because this is also related to 3D vision, because a lot of people working on 3D vision, and a huge part of 3D vision is about reconstructing. But then we see next on this kind of processing, right? Smoothing, remeshing, parameterization, right? Using deep neural networks, and also printing, right? The design, right? The printability, right? So, like, could you share some thoughts on those parts?
Yeah, I think it's kind of interesting that in computer vision, basically all the sort of traditional techniques, maybe barring like a few very rare exceptions, are kind of have been wiped out by deep learning. And there's like almost no competing. But like on the other hand, in geometry processing, I don't think that's the case. Like I think that still a lot of the fundamental techniques are still outperforming the deep learning ones. And for me, I think that's exciting because it feels like there's a place to still innovate. I don't know, like it's a good question whether it will ever like overcome it completely. It's hard to say. Yeah, I don't know.
View that there's a huge space to innovate, right? I think part of research is that the opportunities, also challenges over there. Yeah. Yeah.
Searching for the interesting problems.
Yeah.
Yeah, I think you guys brought up a point about this relation to like how ImageNet was pushing the field of 2D images forward, and I kind of feel like maybe not exactly a question, more of like just hearing your opinion on that, because I feel like in some sense that was because a lot of time in images people were concerned about like classification tasks. So an image is assumed to be reconstructed, right? There's no missing data there until we start talking about multi-view, right? And then we're actually interested in the underlying 3D scene, whereas like a 3D sensed scene is almost always assumed to be not reconstructed until we kind of declare, hey, here it's reconstructed because we have a mesh, right? So the task of classification is one, clearly, but I think a lot of the effort in geometric deep learning in your works, we see that a lot is about, here's my input data, but that's just not enough, right? So labeling it would be just half of the game. You know, the real game is like, oh, how do we make it usable? How do we actually, you know, make something we can print in a 3D printer, right? Or render from using a renderer.
Yeah. No, those are very good points. I mean, I think like there's a fundamental difference between data collection of images, which is just like, I don't know, gathering them, right, and assigning them a label, and segmentation is a little more involved. So you have to have like someone sit there and per pixel, I guess, assign values. But for, geometry in 3D, there's like so many more steps to even get to the point where we're thinking about classification, and then moving beyond classification, more like synthesis. So already it's really challenging to generate 3D shapes. Like these tools are not super intuitive for most people. So like that process of requiring from sort of acquisition all the way up to synthesis is challenging, I think, to acquire the same scale of data for sure. Plus, we need more data because we have the third dimension, right?
So looking, you know, as like a follow up on that, you know, looking at your first part of the talk, you were showing different ways in which you can basically generate free supervision from your signal, right? So you took, you know, a bunch of point clouds, you maybe, you know, focused on the sharper regions, and then you try to train a network, you know, to displace the points to focus on the sharper regions. You know, it reminded me a lot of like what was self-learning like in images, right? In like generating free supervision, right? So these methods now seem to be dominated by contrastive learning, right? And I guess my question is like, do you see, because again, we're not lacking 3D data, we're lacking, you know, good annotated clean 3D data, right? There's lots of lighter data sets out there that we can use, and still I don't know if there's enough work on like you know, using that real data to generate like good self-supervised pre-trained features.
Yeah, that's interesting. Definitely, by the way, the inspiration for the consolidation came from those techniques and images. I think specifically it was maybe the adverse. I mean, it's not really related. I don't know why I felt inspired by it, but like this idea of the adversarial expansion, where you take a single image and you look at a smaller patch, and then you learn to do this like from smaller to larger, like within the single example. And yeah, so I guess you're saying that today the better way to do that is just learning some representation like in a self-supervised way with like some contrastive information. But I suppose the assumption there is like that you have a ton of images that represent kind of the underlying thing that you're interested, like the manifold of natural images at the very least, or even more specifically like human faces.
But also very aggressive augmentations, I guess is what I'm saying. Like when you look at you know, Scene Clear and all of the learning works, their augmentations are like, they're going way beyond like what we'd expect to see in a natural image. Right?
Yeah. That's interesting, because I think I saw a work by Noah Snavely about this idea of like these reflections. So there is a bias, like when we see, he showed like a coat hanger, you know, we could detect sort of like what seemed reasonable. Just so the implication there is that like flipping or vertically or horizontally is losing important information. And yeah, I wonder like.
Yeah, I guess if you take a medical image and you know, not a lot of people have their hearts on the, you know, right-hand side.
Yeah. So I don't know, like, but I mean, I guess you can't argue with the results. I suppose it's just, maybe it's a little myopic way of thinking about the problems, because it's like, okay, we could just take the data, we can do all these things, and then the network's going to learn like stronger and stronger representations. But then like what's that? Like, right, like what's the end game? Just like continue to collect tons of data and just like use that to solve every problem. So yeah, maybe that's just like wishful thinking. But I guess I hope there's like another way around it.
Okay, great. Yes, thanks all for the discussion. I think maybe we should wrap it up.
Yeah.
So yeah, thanks in particular for sort of Qixing and Odd for being panelists and asking great questions. And of course, thanks Rana for a great talk and answering all these questions.
Thanks. Thanks.
Okay, thank you guys. Yeah,
Thank you.
Thanks,
Okay.
Thanks, Rana.
Okay,
Thanks,
bye bye.